right, so we're on the last section of this unit. Heats of formation and calorimetry. All right, so what we're going to do is we're going to study a chemical reaction a little bit more in depth. All right, so we've got ourselves the chemical reaction we've been working with all unit. Methane combustion. CH4 and O2 gives us H2O and CO2 plus 802.3 kilojoules of energy. It's an exothermic reaction because our energy is on the product side. The energy is leaving the chemicals and going to the environment. So whenever we see a chemical reaction, our first thing to do is to balance it. C's are balanced. H4H2. There's two of those. O's, we got 2 on this side, 4 on this side. We need 2 here. 1, 2, 2, 1. Make sure to put the 1s in, because when you get to a Chem 30 final, they might ask you for the coefficients of an equation that's balanced, and you need to include the 1s. So what's going on in this reaction? Well, we've seen this already. We start with the CH4, right? CH4 looks kind of like this, methane. And then we've got 2 O2s. Right? Then we have to put some energy in. Energy in. So the energy goes into the chemicals to break them apart. Now, I'm going to do a reaction pathway diagram, just a rough one. It's not a real one with real numbers. So here's our products, our reactants, sorry. Here's our reactants. Now, we're putting the energy in. And it makes up to this intermediate step where everything's broken apart. We got some C's and H's floating around and 4 O's in the mix. That's 3 O's. Now we're in this activated complex phase of the reaction. Now, energy is going to go out. As the bonds form, they release energy out. So then energy is going to go out until we get down to our products. And our products are the 2 H2O's. There's one. There's another one. And a CO2. Now, as you can see, we put a little bit of energy in and we got a lot of energy out. Now, the net change in enthalpy of the reaction is negative 802.3 kilojoules, which means our reactants had 802.3 kilojoules more energy than our products. And so we start off with our reactants, put some energy in, broke them up to get our activated complex, then energy started leaving as our products were formed. Okay, so breaking apart chemical bonds takes energy. It's an endothermic process. Forming new bonds releases energy to the environment. It's an exothermic process. So, what does this all mean? Every substance has a set amount of energy in their chemical bonds. This energy can be represented by the heat of formation. And we have a chart. Standard enthalpy of formation looks like this. This tells us how much energy is held in the bonds. So you can see we've got Ag2O up here. There's negative 30.6 kilojoules in 1 mole of its bonds. Basically what this means is, in order to make Ag2O from just Ags and Os, so if you've got Ag2O and you want to break it apart into an activated complex, you have to put in that much energy. If you have an activated complex of Ag2O, so you just got some Ags and Os floating around, and they form Ag2O, you're going to release that much energy. So you can see we've got all kinds of chemicals on this sheet. We'll learn how to use that. The heat of formation of pure elements is 0 kilojoules, as there are no bonds to be formed. When we break up a compound, the delta H will be positive. Right, I'm going to do that in purple, because it's an endothermic process. It takes energy from the environment to go into the chemicals to break them apart. Right? So we have to put energy in. When we put the compounds back together again, it's an exothermic process because energy is getting released from the chemicals into the environment. All right. Now, using the table of standard enthalpies of formation, identify the heat of formation for each of the following as an example. All right, so we're just going to use this. Liquid water. Where is liquid water on here? Well, you find H2O and you find the liquid. It's negative 285.8. And that's kilojoules per mole. I really have no idea why that's there. I don't think that really gives us anything. Oh, I'm missing a backside of this. Yikes. Iron 3 hydroxide. Do you remember what iron 3 hydroxide is? It's going to be something with Fe, isn't it? And if I'm looking on this, I do not have anything with Fe on it. That's the back side of this page that's missing. Oh no, there's some Fe. We got Fe3O4 and Fe2O3 right here, but not iron 3 hydroxide. So we can't do iron 3 hydroxide. Generally, we're not going to be able to deal with... oh boy, this is kind of bad. Not going to be able to deal with ionic substances without the back. Propane's on here, though. C3H8. Negative 103.8 kilojoules per mole. Sulfur trioxide is right down here. Sulfur trioxide, negative 395.2. kilojoules per mole. What's this one? Calcium. Just plain Jane calcium. It's elemental. So it doesn't have any heats of formation. Strangely, nitrogen gas, N2 also has 0 kilojoules per mole because it's naturally diatomic. Right? You don't find any N2 on here. You don't find any O2 on here. You don't find any of the diatomic substances. Now, all the examples that we are going to do are going to, well, hopefully have, what do we call them? Molecular substances on them. So they're all going to be molecular, and we're not going to deal with any ionic compounds. All right, so what is the heat of formation for 2 moles of water? So we're going to do 2 moles of water using this chemical reaction. Oh, that's right. What's the heat of formation for 2 moles of water? Well, we go water in liquid form is negative 285.8 kilojoules per every 1 mole. So how many kilojoules will that be for every 2 moles? Well, we just multiplied 285.8. And my calculator's way over here again. Oh, I hope you hear that chair squeaking. It's a lovely sound. So, 2 times 285.8, 571.6 kilojoules of energy for 2 moles. Now, this would be negative, right? Because forming chemical substances is exothermic. So now, what we're going to do is we're going to do the heat of formation for this chemical reaction. Now, some textbooks and some YouTube videos will give you a big, long formula that looks really complicated. And guess what? It's stupid. You don't need a formula. Using a formula when you don't need one is always a bad idea. Using your brain and logic is a great idea. So we're going to take a look at this. We got this chemical reaction, right? 1, 2, 2, 1. So we use our chart. And we look at the heats of formation for CH4. And we got CH4 right here. It's negative 74.8. So it's 74.8 kilojoules per mole. Now in this case, it's actually going to be positive because we're breaking it apart on this side. So it's going to be positive. And there's 1 mole, so we times it by 1 mole. Oxygen, not on here. It's diatomic, so it's 0 kilojoules per mole. And we multiply by 1, by 2. 0 times 2 is 2. So we're going to figure out, what we're figuring out here is how much energy it takes to break all these guys apart. How much energy does it take to break all these guys apart? Then, on this other side, we're going to figure out how much energy do we get from them going back together. Let's just cross this guy out because we don't want to look at this guy. So we've got H2O. Now, this H2O is most likely going to be a gas. So we're going to get negative 241.8 kilojoules per mole times 2 moles, because there's 2 moles of it. That's what that number is. CO2, come on here and you find CO2. I sure hope we can find CO2. CO2 gas, 393.5. Right there. Negative 393.5 kilojoules per mole times it by 1 mole. Okay, so now we figure out how much there is in total on the reactant side. We do 74.8 times 1, and then we add 0 times 2. So 74.8 times 1, it's just 74.8. So on our reactant side, we took us 74.8 kilojoules of energy to break everything up. On the product side, how much energy do we get back? Do we give up? Do we give out when we are forming these chemical bonds? Well, I do 241.8 times 2. This is equal to 483.6. Then I add to that 393.5. And I get negative 877.1 kilojoules of energy. So it took this much energy to break everything apart. We got this much energy when we built our new compounds. Okay, so all right, so let's finish our total delta H. To figure out our total delta H, we just add these two numbers together. We do plus 74.8, right? This is the amount of energy it took to break apart, so that's an endothermic, so it's positive. Then we add to it our negative amount, 877.1. And that's an exothermic. We're losing that energy when the new chemical bonds are formed. And we add them together. And we get, surprise, surprise, we get a delta H for this reaction equal to negative 802.3 kilojoules. Ah, magical. That's this number from up here. That's where that number came from. It came from this chart. Now, if I'm going to draw a quick little reaction pathway diagram for this reaction pathway diagram is not going to be to scale. Our reactants are blue. It went up this distance was 74.8 kilojoules. That's how much it went up. It went up to 74.8 kilojoules, and then it dropped down 877. That's how much it dropped down from there all the way to the bottom. Now what that means is our delta H, our overall change in energy from here to here, is negative 802.3 kilojoules. All right, so in the next video, we'll look at some examples on how to do this, and you should be able to do this on your own.